Greetings, students. On the 14th of July of 2023, Professor Penn published a video where he showed four proofs for the Euler's formula, which is e to the I theta equals to cosine of theta plus I sine of theta. And here I'm going to present a fifth way for proving this identity. And for that, I'm going to take the right-hand side and set it equal to z. So z is cos theta plus I sine theta. And now I'm going to differentiate both sides with respect to theta. So we get dz by d theta equals to negative sine of theta plus I cosine of theta. And if we factor out an I from this expression, we get negative 1 over I times sine of theta plus cosine of theta. And if you multiply 1 over I by I at the top and bottom, you get a negative I over I squared, which is negative I over negative 1, or just I. And we get this as I times sine of theta times I plus cosine. And this expression inside the bracket is exactly our z. So we get dz by d theta equals to Iz, which is a very simple first order separable ODE to be solved for z in terms of theta. And if we divide both sides by z and multiply by d theta, we get dz by z equals to I d theta. And if we integrate this, we get natural log of z on the left equals to I theta plus some constant c1. And then we can write z as e to the I theta plus c1, or e to the c1 times e to the I theta. But e to the c1 is just some constant, so we can write this as c times e to the I theta. And to evaluate c, or the constant of integration, we need to evaluate z at some theta, and what is better than theta equal to 0. And we know that z at theta equal to 0 is cosine of 0, which is 1, plus I sine of 0, which is 0. And to get the same value of 1 from c times e to the I theta at theta equal to 0, c must be equal to 1. And that's the end of the proof, and we get z equals to e to the I theta from this integration, and also equal to cos theta plus I sine theta as defined in the very beginning. But there's a nice application with this formula which I really like, and it's that it actually gives us a very quick way for writing the expanded version of expressions like sine of n theta or cosine of n theta. And it's actually a shortcut to using sum and difference identities. I'm going to show it to you by an example. I'm going to get the expanded version of sine of 3 theta and cosine of 3 theta. And we can get both in actually one shot. So we know that e to the I theta is cosine of theta plus I sine of theta. And if we just change theta to 3 theta, we get e to the I times 3 theta equals to cosine of 3 theta plus I times sine of 3 theta. But e to the I times 3 theta can also be written as e to the I theta raised to the 3, which is cosine of theta plus I sine of theta, the quantity raised to the third. So in these two expressions, the left sides are equal, so the right sides must also be equal. So we get cosine of 3 theta plus I times sine of 3 theta equals to cosine of theta plus I sine theta, the quantity cubed. And if we apply the binomial expansion formula to the left side, we get cos cubed of theta plus 3 times cos squared theta times I sine theta plus 3 cos theta times I sine theta, the quantity squared. And then the last term is I sine theta, the quantity cubed. And that's equal to cosine of 3 theta plus I times sine of 3 theta. Okay, so we have two real terms here. Since here I sine theta quantity squared is negative sine squared. And two imaginary terms, one is here, which is 3I cos squared sine, and this I sine theta, the quantity cubed, that is I cubed times sine cubed, but I cubed is I squared times I, or negative I. So this is negative I sine cubed of theta. So if I kind of separate the real and imaginary parts on the left side, for the real part we get cos cubed of theta minus 3 cosine of theta times sine squared. And for the imaginary part, we get plus I times the quantity 3 cos squared times sine minus sine cubed. And we have cosine of 3 theta plus I times sine of 3 theta on the right as before. Obviously, the real parts on both sides must be equal, and so must be the imaginary parts. So we get cosine of 3 theta as cos cubed of theta plus 3 cos squared times sine squared of theta. And we also get sine of 3 theta as 3 cos squared sine minus sine cubed. And in my opinion, this is awesome and incredibly fast. At least much faster compared to using the sum and difference identities. I hope you liked it too, and I wish you will have a good day. Thank you so much, and see you soon again.